Okay, welcome everyone to the sequencing and pre-confirmation call number 6. This call is going to be about real-time proving and real-time settlement. I have a presentation which I prepared, which I gave at ZK Summit a couple of days ago. I guess this is an opportunity to give the presentation to those who haven't seen it, but more importantly, for folks to ask questions and to have hopefully a lively discussion around it. So do feel free to interrupt me as we go. Unfortunately, I don't have a great connection. I'm on a mobile connection, so I decided to turn off my camera, and I'll go ahead and show my slides. Okay, so I'm going to be talking about real-time proving, which to a large extent is all about ZK ASICs, SNOC proving ASICs. And the three parts of my presentation is, first of all, about giving motivations as to why real-time proving is valuable, why we want it, and it actually goes way beyond synchronous composability. Part two is to try and give you a sense for the progress on SNOC ASICs, and I'll be able to show with you when I turn on my camera the first ever SNOC ASIC. And then in the third part, which I guess we could go through very, very quickly, because I think it's slightly less relevant, is my opinions on what is one of the best designs for a SNOC ASIC. Do let me know if you want to ask questions. Just interrupt me. No need to raise your hand. Okay, so motivation. I guess before the motivation, I want to give a quick definition. In my mind, real-time proving is when the proof latency, meaning the amount of time it takes for a proof to arrive relative to native execution, is less, ideally significantly less than the slot time. And so because we have a slot time of 12 seconds, the 10-second kind of ballpark is the minimum that you need to qualify as real-time proving, but ideally we'll get much, much lower, 1 second, 100 millisecond proof latency. And as we all know, real-time proving is one of these things that allows for synchronous composability. And the slide that I want to show you here is this one, where I've introduced a new term, which I call the synchrony window. So if we have a proof latency, for example, of 1 second relative to a slot duration of 12 seconds, then our synchrony window is 11 seconds. And the reason is that it takes 1 second to generate a proof, and I need to include a proof in my block as a sequencer. Then I need to start the proving process 11 seconds in. And so my opportunity for synchrony is limited to the synchrony window of only 11 seconds. And so what I think will happen is that initially we'll have real-time proving on the order of 10 seconds. And that will mean that the synchrony window will only be the very first 2 seconds, which is probably the most valuable part of the block because it's the top of block. But eventually we'll be able to squeeze out more and more synchrony out of our blocks. Now, one thing I do want to highlight is that, sure, we can use SNOCs here for this real-time passing of messages, of trustless messages. I'm going to be muting a couple of people. But we can also use another technique, which is a slightly less trustless and more collateral inefficient, which is to use a liquidity provider. So instead of actually passing assets immediately and trustlessly through a shared contract or through some sort of deposit contract or through the R1, we can also use liquidity providers that kind of simulate this. So the liquidity provider here in the middle can immediately send tokens and assets on the desired rollup to simulate synchronous composability, even though the dash lines here, the green dash line and the green dashed yellow line, can take a very long time, for example, 7 days. So this is kind of interesting, for example, for optimistic rollups or even ZK rollups today that don't have real-time proving. And so what I expect will happen is that we're going to see these liquidity providers fill in the gap, hopefully in a few months. And then whenever the hardware is ready with real-time proving and everyone has opted in, then we won't need those liquidity providers anymore. Yeah, of course, there's downside to liquidity providers. There's fees, intimidation, and liquidity constraints. And it also doesn't work with things like NFTs very well. Now, the second big opportunity for real-time proving is this idea of light validation. So we have a notion of a big node with builders, relays, and provers, and the notion of a light node, users on their mobile phone or on their smartwatch. And right now we have this awkward kind of sitting type of node, which is the validator node. And they're medium nodes in the sense that they can't run on the phone, but they don't need that much hardware. A laptop is sufficient. And what I think will be happening is that one by one, the clients will become ZK clients. So Geth might become ZK Geth, and Besu might become ZK Besu. And in order to become a ZK client that is useful for validators, you need to have real-time proving. And the reason is that when a new block comes in, you need to know within a few seconds whether or not it's a valid block so that you can sync up with the tip of the chain. And so, this is a key step in individual clients becoming ZK clients. And one of the nice things here is that it's purely off-chain, right? You have different client teams, or even teams outside of the client team snarkifying the client teams. And actually, we have a couple projects. I think Risk Zero and the Succinct team that have been able to run ref on top of their platform. So they've already been able to snarkify a whole client like ref, and the provers are able to keep up with the chain from a bandwidth standpoint. And now we're down to latency optimizations. Now, once we have a ZK client for every client, which has real-time proving, we're going to be in a position where we can introduce this really cool precompile, which I call the EVM in EVM precompile. And it basically allows for EVM execution within the EVM. And what this precompile takes as input is a pre-state, a post-state, and a state diff, and some proofs. And it returns true or false, depending on whether or not the state transition between the pre-state root and the post-state root is a correct state transition corresponding to the state diff, and the proofs are indeed valid cryptographic proofs for this statement. And one of the interesting things here is that it's a very strange precompile because one of the inputs is an implicit input that is submitted off-chain, and it's done on a per-client basis. So Geth, for example, or ZK Geth, might have a specific proof system that it has adopted, a specific circuit that describes the EVM, and it may have a certain performance characteristic, it might have bugs and whatnot. And if I'm running ZK Geth, I will have to verify the ZK Geth proof. If I'm running another client, I'll be verifying my own client. So the advantage of keeping these proofs off-chain is that we can have client diversity. We don't have to enshrine any specific proof system. It also means that the clients can just continuously update their proofs without having to do hard forks. It's just a very, very clean design, which is pretty much the same that we have right now, without the ZK part. And if you're interested in the where it's placed in Vitalik's roadmap diagram, it's under the verge. There's a little square here called Explore EVM Verification Precompile. Now, if you are a rollup,
I have a quick question.
Yeah.
Is there any particular reason you chose to write a state diff there?
Yes, great question. So the state diff here is a data availability constraint. So the data corresponding to the state transition needs to be available. And this is a bit of a technical reason, which is that we want anyone to be able to produce proofs for all the clients or for any of the clients. And if the data is not available, then they can't produce the proof. And so, unfortunately, this EVM and EVM precompile doesn't work very well for Validiums because it requires the data to be actually on Ethereum. So, yeah, it's really a precompile that's designed specifically for rollups because the state diff needs to be available.
One more follow-up question. So, for instance, if we are executing a set of transactions, the state diff here includes the effect of the transactions or the transactions themselves, like the signatures and so on, are included here or
It
somewhere
could
else,
be
maybe?
anything. I mean, technically, it just needs to be sufficiently. It needs to be data from which you can calculate the state diff. So it doesn't have to be the state diff itself. It could, as you said, it could also be the input transactions. This is not like well defined at this point. Yeah, the only strong requirement is that it's sufficiently well enough data to be able to recompute the state diff.
Makes sense. Thank you.
Perfect. Now, a rollup that uses this precompile is called a native rollup. And there's a few advantages of native rollups. One is that they're super easy to program. Like it literally is like one line of code, which is in stark comparison to what it takes to deploy an EVM rollup today. You need many engineers and you need to invest a lot of time and effort to build circuits and for proofs and whatnot. The second big advantage is that if you want to have an EVM equivalent rollup, then this rollup is correct by construction. Like you're literally reusing the logic of the clients that secure the L1. So whatever secures the L1 is the exact same logic that also secures these native rollups. So there's, in some sense, there's no way in which there could be a bug. And then a third advantage is this notion of governance synchrony. So the L1 has its own governance, and this in the sense that we can do hard forks and we can change the EVM and add opcodes. And this is a real hassle for L2s that want to stay EVM equivalent because now they also need to do an equivalent change. And in order for them to do that, because they don't have access to the social layer, they have to use some sort of governance mechanism. It could be a multisig, it could be a governance token. And this governance is in and of itself an attack vector. And it might also not be perfect. It might have latency and whatnot. And so one of the nice things of native rollups is that as soon as the EVM at layer 1 updates, all the native rollups immediately update in the exact same slot as the hard fork happens. And then there's this fourth really cool possibility, which is now you can have native rollups without any gas limit whatsoever. And the reason is that the gas limit is there to prevent primarily a denial of service attack on the validators that need to re-execute the block. And so if re-execution is constant time because you have to verify SNOCs, on the order of 1 millisecond, then now you can remove the gas limit. And basically, the only bottleneck is just how fast your computer is running to do the native execution and also to do the proving that corresponds to it. And then once we have these native rollups, in some sense, we've reintroduced the notion of execution sharding, which used to be called phase 2 a few years ago. But it's actually a much cooler version of execution sharding. So previously we had like a fixed number of execution shards. We had 1024 or 64 execution shards. And now here you can have as many execution shards as you want, and it's permissionless, it's programmable. And you can add whatever logic you want around your shards, so or your rollups. You can add governance, you can add tokenomics, you can add public goods funding, you can do whatever you want. So it's a really cool kind of end game to and a much better version of execution sharding that we had compared to a few years ago. Okay, so this is the summary slide of the motivation. What does real-time proving unlock? It unlocks real-time settlement for the rollups, which gives us this universal synchronous composability. It unlocks ZK clients or SNARKs clients, which gives us light validators. This will happen incrementally, one client at a time, off-chain. And then once all the clients have been snarkified, then we can think about introducing this precompile. And this precompile gives us native rollups, and it gives us this native execution sharding, which is super cool. And one of the things I want to highlight in this last slide is that there's actually incentives for, in this case, the block builders to invest in real-time proving, and specifically to lower the latency of their real-time proving. And the reason is that the faster you can do the proving, the lower the proof latency will be, and therefore the greater the synchrony window will be, and so therefore you can have more transactions that are synchronous in your blocks, and those should be denser in the sense that they should be higher paying transactions. Another thing is that the faster you can prove, and by fast I mean the lowest latency, the more time you'll have to build your blocks as a builder. And the reason is that the block needs to come with the proof. And so if you have, let's say, 1 second of overhead to building the proof, well, that's 1 second that could otherwise have been used for block building, but instead is used for proving. And then finally, once we have these native rollups, especially native rollups that don't have a gas limit, then, as I said previously, you're just going to be bottlenecked by physics and computation. And so if you invest in like these, really fast executors and provers, then you'll be in a position where you can literally stuff more transactions in your blocks. And all of these things lead to more MEV, which is an incentive to go invest in real-time proving. Okay, any question in this first section? Okay, so now let me talk about ZK ASIC progress, because a lot of people, their initial reaction is, okay, these ASICs, they all sound great, but like it sounds it sounds also a little crazy and far-fetched. So it turns out that there's a lot of effort today that is focused on these SNARK ASICs. So there's 3 companies, which I guess I'm calling the flagship companies in this context, which are Axial, SciSig, and Fabric. And I call them flagship because that's the only thing they do. Like literally, these companies were created to build one single product, which is a SNARK proving ASIC. And they've already, in some cases, shipped an ASIC. So in the case of Axial, there is already a chip. And there's like a ton of progress that's done by these other companies. And they're also very well funded, and they have a lot of talent in-house. And then there's another crop of companies which are also building ZK ASICs, but for totally different reasons. It's for Aleo mining. So Aleo is this blockchain where the proof of work mechanism is effectively snarkifying some sort of statement, some sort of puzzle. And so through the back door, in some sense, these companies are interested in snarks through mining. And then there's other companies, and I list 5 here, that are interested in building these chips, but they most of them haven't started yet. So, for example, Ponos is one of them. Ingonyama is one of them. Aurodyne told me that they have started the process of an ASIC for a ZK protocol, but they won't tell me which ZK protocol. So I don't know exactly where they fit. Maybe they actually fit in this green category. But all in all, there's a lot of companies working on this. Now, I mentioned that we already have an ASIC, and it's from SciSic. And let me turn on my video so that you can see what it looks like. But yeah, this is basically the bottom. You can see all the pins, and then this is the top of the chip. And this shiny area here, I believe, is the actual die where there's silicon, and it's about 100 square millimeter chip. So it's a reasonably sized chip. It's not excessively large, and it's built using a 12 nanometer process from TSMC. So this is an 8-year-old process. So it's not bleeding edge, but it's also like not too shabby. And so what I expect will happen is that we'll start seeing chips on even better processes. In some sense, this is a test chip. Now, what does this chip do? The way that I think about it is that it's a partial accelerator for SNOC. So when you're proving SNOCs, you have these big workloads, which are called MSMs or NTTs, and this chip will basically do these heavy duty workloads. It also does finite field vector addition and multiplication, and there's some amount of programmability. So it supports pretty much any proof system or like most of them. And the reason is that you can configure the prime in the context of your FFT or your NTT. So if you have the stocks, for example, from Starkware or from zk-sync or from Polygon or whatever it is, then you can configure your prime. And then in the context of MSMs, you can also configure your curve, your elliptic curve, to work with BN254, which is very standard, but also other curves like BLS381. And this is what the Axial board looks like. They've only kind of got it working a few days ago. So they have these 4 chips on the board. It's a PCIe board, and they have 64 gigabytes of memory. So I believe these are the memory chips here, which are connected next to the chips. And this whole board here is a board that you can go plug into a PCIe connection and get acceleration. And this is like the performance that they measured specifically for MSM. And so you can see it's like compared to a 3090 GPU, so that's an NVIDIA GPU, they actually got they got better performance. So lower number here is actually better. And it costs significantly less. So it costs about 5 times less than this GPU. And it also costs roughly 6 times less from a power consumption standpoint. So this board consumes 6.3 times less than this GPU. So all in all, it's a win everywhere. It's a better performance, it's a better cost, and better power consumption. And also, once they're able to like compress this chip and make it, because this is more of a test board, I also think that the size of the board will be much smaller than an actual GPU. Okay, so that's Axial. They've come out with the V0 chip, I guess, and they have plans for new chips already. But there's these 2 other companies. There's SciSic, which is taking a slightly more ambitious approach for the first version of their ASIC, which is a full end-to-end SNOC accelerator. And the reason this is interesting is because even though the MSMs and the NTTs are the major workloads, once you completely accelerate them, let's imagine that they take 0 time, you're still left with other stuff. And so the other stuff starts becoming the bottleneck. And let's imagine that the MSMs and NTTs take, let's say, 80% of the time. You still have 20% of the time, which is other stuff. And so in the best case, if you were to accelerate the 80%, you only have a 5x speed up. Which is good, but it's not the 100x speed up that ASICs really promise. And so SciSic is kind of shooting for this more ambitious kind of 100x. And then there's a company called Fabric that is basically building a cryptography GPU. You can think of it as a GPU but where the individual circuits, for example, the multiplier circuits, instead of being floating point multipliers or integer multipliers that are used in the context of AI, those would be finite field multipliers. So, in some sense, even more ambitious than what CISIC is doing, but also much more complicated. So now they need to come up with their own tooling, their own drivers, their own programming language and whatnot. And so, there's a higher chance of failure, but also potentially huge rewards because it's an accelerator that could work for any kind of heavy duty cryptography, including FHE, not just SNOCs. Okay, so this is the CISIC board. So this is the company in the middle that's building a full end-to-end SNOC accelerator. What they've done for their R&D process is that they've worked with FPGAs, which are basically programmable. You can think of them as programmable ASICs. And they basically have 3 FPGAs per board. So there's 2 boards here. And they connect the boards up into some sort of mesh of FPGAs. And their specific setup has 54 FPGAs. So they have 3 FPGAs per board and 18 boards. And this is the performance that they've measured on their setup. So they can do an MSM of size 2 to the 30. So that's about 1 billion base points and coefficients in less than 200 milliseconds. So in less than 1/5 of a second, which this is an absolutely kind of mind-boggling performance, and similar mind-boggling performance on entities. And so now that they have this FPGA proof of concept, it turns out that the natural next step is to shrink these boards, the whole board basically, into one single ASIC. Actually, they're trying to do something even more ambitious, which is to take 3 boards with 9 chips and compress all of that into a single 100 millimeter ASIC. And the reason is that on these FPGAs, they're only using like very specific parts of it, and so they can compress all of that into one really super high performance ASIC. Okay, now the second crop of ASICs is the Aleo miners, and so Aleo should come to mainnet fairly soon. I had a call with Howard, and he seemed fairly optimistic. And the way that I think about it is this continuous Z prize. So for those that don't know, Z prize is an annual prize that actually Aleo was involved, I believe, in the founding of the prize, and it's millions of dollars. It's something like $5 to $10 million every year in prizes to accelerate the state of the art of these of the SNOC proving. And here we potentially have a Z prize which is 10 times the size or even more. So instead of $10 million a year, it could be $100 million a year, or even hundreds of millions of dollars per year. And what I expect will happen is that these companies that I listed at the beginning, the 4 of them, as soon as the Aleo puzzles have been fixed in mainnet, then they will engage in this 6-month race. Because what Aleo has done is that they've used certain puzzles for their testnets, but they've explicitly said that they're going to use a different puzzle for mainnet, which they haven't yet disclosed. And so there's no point to build a ASICs for the testnet puzzles. So everyone's waiting eagerly for the mainnet puzzles. And what I expect will happen is that instead of having just 3 companies that are dedicated to SNOC ASICs, we're going to have roughly 6 companies. And so that's going to be a fantastic outcome from an incentivization standpoint. Okay, any questions on part 1 or 2 so far? Okay.
Okay.
So
Sorry to interrupt. Okay, I'm from Axios. So thanks for having me. Just want to clarify one thing about our chip and the roadmap of CISIC. Yeah, we also consider, because in the acceleration of SNARK is also within our consideration, because because we included the vector addition and multiplication, although also you can operate three operations at the same time. So you can add one variable and the second and multiply with the third variable. So actually we can also support the end-to-end acceleration. Yeah, because you can send the vector into the DDR and to do the MSM or NTT, and then you can let this stay in the DDR and then do the MSM later.
Oh, I
So
see.
in
Very
this way, we
interesting.
can also So you don't have to transmit the data in and back from the host every time you call the MSM.
Okay, that's very good to hear. I didn't actually know that. So yeah, one of the downsides, for example, of doing acceleration on a GPU of MSMs and entities only is that you send the data over to the accelerator and then you get the result back. And then all this back and forth between the so-called host, which is a general purpose, computer with a CPU and the accelerator, that causes a lot of overhead. But what you're saying instead is that the host can send all the data in one chunk, and then it will get stored in these DDRs, so presumably the 64 gigabytes of memory, which has like super fast interface to the chips. And then whatever operation you want, it could be additions, multiplications, entities, MSMs, you can do it all without communicating back to the host.
Yeah, not necessarily all the data. I mean, because sometimes when the circuit size got very large, it's impossible to put all the witness in the DDR. So for small size circuit, we can put all the witness in the DDR and do everything. I mean, the whole snark proving inside the chip, and then send the proof back. But for larger ones, we can use the data concurrency. So we can send the data inside and do the computation inside at the same time. So we can save a lot of time to reduce the communication cost. Yeah. So
Okay.
anyway, we are already developed software. Customize the software that we can accelerate the project and the proof system with very fast in the proof generation. Yeah.
Okay, understood. Thank you so much. This is super helpful. So I guess what you're saying is that if you're bored with 64 gigabytes of memory, well, obviously, if your data chunks are bigger than 64 gigabytes, then it won't all fit in memory. But I guess one nice thing here is that we can just design a new board with, maybe 128 gigabytes of memory, because that's separate from the process of building the chip, which is the hard part. And then another thing, which is an Mhm.
Yeah, that's one way to do it, but it's not the optimal way. We actually, for the next generation chip, we are considering another way because we allows the chip-to-chip communication. So we can have two chips that each support 64 gigabytes memory, and then we can let them communicate with each other, and then we can do a very large entity together, and then we can also start store the data. The first half in one chip and the second half in another chip. Yeah, but that's for next generation. For this generation, we can use the data concurrency. We can, when doing the computation inside the chip, we send the data in and out, so that we can reduce we can hide the communication time.
I see,
Yeah,
understood.
and
So you're
anyway,
saying that
it's yeah.
okay.
Yeah. There are
No,
two
this
ways
is great.
there are two ways to accelerate end-to-end proof generation, because the most important thing is to reduce the communication time. Yeah, because the communication time is kind of smaller.
Okay, gotcha. So I guess Hussein is saying that generally speaking, when you want to prove these very large knocks, you're bottlenecked by communication, which is to say, input output or bandwidth between the host and the chip, the accelerator, or even within the
Yes.
accelerator. And you're not bottlenecked by doing the actual
Yes.
computation. And there's all sorts of tricks like
Yes.
sending the data while you're doing computation on some other stuff. But there's also the next generation, which will allow even better communication from chip to chip.
Yes. Yes. Exactly.
But nice. But I guess one of the things that you said is if we have small amounts of data to start with, then we're in a very luxurious position and hardware acceleration becomes much faster. And this is one of the things that I want to talk about in my opinions about how we should be thinking about real-time proving and acceleration. And in some sense, this is a co-design between the hardware part and the cryptographic and software part. Okay.
Just before we go on the opinions part, so I'm Mami from Taiko, and yesterday the Halo 2 team at VFM Foundation, PSC, Progressive Scaling Explorations, merged something called the ZK acceleration layer. So we started with MSM, and NTT will be next. And the idea was to provide a standard in Rust, a Rust trait, so that people in working on hardware just have to implement this trait, and they would support, well, for starter, Halo 2, but hopefully this can be adapted to Arcworks. There is not much to, implementing the traits is really easy. Arcworks can have their own version, and there is just a small adapter. And similarly, Halo 2, people using Halo 2, so you have, in terms of product, you have Scroll, you also have ZK coprocessors like Axiom, you have Taiko, of course. And you even have companies like, I think, Chroma with Tycoon that are doing Halo 2 compatible in C++. But anyway, this is a standardization for ZK acceleration. The next step will be MSM, and NTZ, sorry. And it actually also supports caching inputs. So either the base point or the coefficients or both, because, well, that was a common feedback that communication was critical. I will send a link to the PR and also to the Telegram chat if you want to discuss it. I think most of the hardware providers like Superscala, Fabric, and Sizic are already in. Yeah.
Okay, thank you so much for this note, Mami. Yeah, once we have standardization, this will basically make the lives of the accelerators so much easier because we can build, drivers and tooling to specifically match this API, and we'll be able to go to move forward faster. Okay, ZK ASIC opinions, which actually have some implications on what kind of proof systems and statements we want to be proving. So just as a quick 101 on SNOCs, there's two parts to a SNOC. There's the front end and the back end. And the way that they're connected is through the witnesses. So you have the front end, which generates the witness, and we call it witness generation. And then you have the back end, which consumes the witness and produces the proof. And this is where the MSMs and the FFTs and the other stuff happens. And just as a rule of thumb, like these witnesses are enormous. So from a data standpoint, they're extremely large, hence the big fat red arrow. And so if you want to minimize the cost of just communicating and moving around this witness, you want to be doing it on chip. And so my first opinion is that really we want to have one chip which does everything, both the witness generation and the proof generation. Today, the way it's done is that the witness generation is on the host, external to the accelerator. And then, as was mentioned by Hussein, we're in a position where this big fat red arrow is slowing us down. So what comes into the chip is the statement, which is a fairly small statement with a thin green arrow. And then what comes out is also very small. It's a small proof. And all the high throughput stuff stays within the chip. Okay, opinion number 2 is that really we want to be dealing with bite-sized chunks. And this goes back to this concept of memory. Like if we have a very big statement that comes in, then that's going to lead to very high memory requirements. And so what I suggest here is that instead of sending the statements, the native statements to a specific application, you send in bytecode. And bytecode basically implicitly means that there is a virtual machine here that works a little bit like a CPU that has clock cycles and ingests this bytecode. And every clock is a tiny chunk. And this is what many teams are doing. They're working with, for example, a RISC-V virtual machine, or for example, Starkware has the Cairo virtual machine, which is pretty well known. And because you're working with these small chunks, it's memory friendly. And so it makes the construction of these chips much more feasible. And then in order to have like lots of small chunks, you need a way to stitch together the chunks. And this is where recursion comes in. And there's like the fancy name for recursion is PCD, proof carrying data. And there's also this other term called continuation. So you do a bit of computation, and then you continue it with another piece of computation, and you continue it again and again and again. And we basically need proof systems that are friendly to continuations. So that's opinion number 2. And then opinion number 3 is that we really want to be doing as much programmability as possible out of the ASIC. So programming chips is like very, very complicated. Having chips that are programmable is very complicated, but doing programmability in software is like 10 times simpler, if not 100 times simpler. And the nice thing is that if you have a virtual machine here, which is general purpose, like Turing complete, then you can send bytecode here that can really represent any statement. And so if you have some sort of high level application, which is written in Rust even, or some other language, and you have some sort of action that generates a statement, well, that's fine. The ASIC can handle anything, right? Because here you basically have a general purpose virtual machine, which is consuming the bytecode. And then another kind of concern is, what about the programmability of the proof system? So oftentimes you have hardware manufacturers like Axial that are worried about the community not adopting their chip because it might not be programmable enough. And so what Axial did is that they're allowed to configure the curves and the primes and all of these things. But my opinion actually is that all of this configuration should happen in software. And the reason is that there's a notion of a wrapper SNOC. So you have some sort of internal SNOC that you want consumed in a smart contract, but the smart contract has constraints. For example, if you want really low gas costs, you need to be sending in a so-called BN254 proof or Graph16 proof. And so many different projects nowadays have this his design where basically they take an internal proof and then they wrap it to generate a wrapper proof, which I call a wrap for short, and then they send that in the smart contract. And the nice thing about the wrapper proof is that it can translate between proof systems. So you can go from Starks to Graph16 or whatever to Graph16. And so what I think should happen is that the hardware manufacturers should be very opinionated on the proof system here, one that is friendly to continuations, friendly to memory, friendly to hardware, friendly to all these things. And then whatever they use, it doesn't matter because you can abstract it away with your wrapper SNOC at the end. And so in some sense, that what the hardware manufacturers can do is that they can provide some sort of drivers or software to do the wrapping at the end so that you can consume your proof on chain. And if you look at the top rollups today, they're optimistic rollups. And the teams don't have any knowledge about SNOCs. And so they don't really care, what curve or what proof system. The only thing they care about is that you can give them something that works and is cheap to verify on chain. And so I think it's perfectly fine for the manufacturers here to be opinionated on the internal proof systems that is used. And then the fourth opinion that I have is you want to be embracing some of the standards of the industry. So one of them here is Graph 16. This is not super relevant because it's part of the software stack. So worst case, you can just have a different wrap. But maybe the most important one here is the RISC-V bytecode. So if you want to be sending in RISC-V bytecode, then you need to have a RISC-V virtual machine in here that needs to be baked into the ASIC that can't change. And as far as I can tell, RISC-V seems to be the winning virtual machine. So there's Succinct with SP1. There's Nexus that's doing it. There's Jolt from the A16Z team that was announced very recently. There's RISC-0, of course. And so I just tend to really like the RISC-V virtual machine. It's kind of this. Go ahead.
I could see some how do you say, pros to also WASM, if only for browser-based proving and web GPU as well.
Yeah, absolutely. And there's also merits for ARM as well. I think there's like basically a trade-off space depending on the complexity of the virtual machine, as well as web.
I think ARM is a bit too complex, so it's very nice for programming, but the fact that it has a status flag, for example, addition with carry, makes it, I think, I'm not a hardware expert, but more painful to implement in FPGA or ASIC. But if we can have ARM, we can make it much faster because add with carry is really painful when you program for elliptic arithmetic. But it's not a problem for Starks though.
Yeah. So I mean, my guess is that in the short term we're going to see like these super simple instruction sets, like RISC-V that I believe only have like 40 opcodes. And then we're going to go up the complexity stack, maybe with WASM and maybe with ARM. I'm told that ARM has now 1,000 opcodes. It's no longer a simple instruction set at all. But one of the interesting things, I guess, thinking fundamentally, is that the proof system, the proving should not be the bottleneck eventually. And the reason is that you can massively parallelize it. And so you're going to be bottlenecked by the native execution. And then the question becomes, okay, what is the fastest native execution that you have? What is the fastest CPUs? And it might be the M3 CPU from Apple, and that turns out to be an ARM CPU. So maybe in 10 years' time, I would change the slide to ARM. But in the meantime, it seems that kind of in the short and medium term, RISC-V or WASM might be a good answer here. Okay, opinion number 5, which in some sense is a continuation of opinion number 3. So if we have the programmability that's off-chip, but then on-chip, we can just fix everything. And this is why there's the frozen emoji, because you're kind of freezing the logic that's internal. And when you freeze, you can pick a specific prime, a specific curve, and you can really squeeze as much juice as possible. So for example, in the case of Axial, they have these 384-bit multipliers. And so if your prime is 256 bits, well, now you've kind of wasted a bunch of die area, and you're consuming a needless amount of power just to support these larger primes. But even with 256 bits, if you were to fix a very specific prime, then you could get another kind of maybe 2x. So the kind of potentially a 4x difference between having programmability of the prime versus not having it. And then also just building a chip which is not programmable is just so much simpler than building a programmable.
Sorry to interrupt.
Go ahead, please.
I have 2 questions about this architecture. So the first one, that do we do the bottom level proof and the recursion in the chip?
Yes. So the recursion actually comes into two places. One is that it's internal to the chip. So you have these cycles that come in, you have these little chunks, and you have to glue everything together. So there's some amount of recursion in the chip. But the other cool thing is that there can be recursion that is cross-chip, and that allows you to scale horizontally. So if each chip can only run the RISC-V CPU at, let's say, 10 megahertz, but you really want to run a system at 1 gigahertz, so you can basically have 100 chips that are horizontally scaled, and they all stitch together with these continuations that they produce.
Okay, I see. Great.
Yeah, so like
Uh, the-
I can elaborate a bit more on this question. This is Leo Fan from CESIC. Yeah, so like actually like we started the ZK VM paired hardware design sometime last year. Yeah, so we found it like very hardware friendly, like in like several aspects. The first is due to this like continuation, which means you can basically slice the execution like into like several like segments, and each segment they are like independent of each other. And second, the I/O bandwidth like for each segment is like very sweet. Yeah, so it's like around 15 megahertz in, 250 kilobytes out. Yeah, so like minimum bandwidth. And the third thing, which is also like very good, is like the memory requirement like for each proof generation, like on each like accelerator is fully controlled by you. Like you can tweak the like the size of the segment to make sure like you just have enough memory like to support the proof generation there. So this like three things, like yeah, we have like our own ZKVM design, which we borrow a lot of ideas from succinct RISC-0. Yeah, and we have developed the corresponding hardware component to accelerate it.
Amazing. Thank you, Leo, for your point of view, and thank you so much for being one of those companies that's focusing on solving this problem.
Okay, I have a second question as well. Okay, so when we accelerate the proof generation and the recursion fast enough, will the growth 16 rep be the bottleneck? Because as far as we know that in order to get the small proof size on chain, they tend to make growth 16 very large in size.
Yeah, so like I can probably like also talk a little bit more on that part. Yeah, so after like each proof generation, you get like a proof, like the proof of your choice. Like you can have like fry proof or like the other proof. Then you have this like 2-to-1 recursion. So like you recurse a lot. You basically build a Merkle tree of proofs. And after that, probably like the last step is the growth 16. Like you just wrap it up and then put it on chain. Yeah, so the last step, like it depends on like your design, or like it depends on the finality that need from your customers. So like there are a lot of like factors like you can take with.
Oh, but my question is that the two part in this architecture, the first proof generation and the final proof generation, the cycles growth 16, they are totally different because they have the first is wide and low in size, but the second is very tall, and it's small in. It's a narrow tall thing, and but the first is the wide smaller thing. It's totally different, especially for the entity, right?
Yeah, so you're right, Houston. Like from a proof system standpoint, these are completely different proof systems. And what the wrapper
Yes.
does, in some sense, is a translation between the proof systems. Now, one thing that Leo said is
So
that you only have to do the wrapper snark basically when you want to settle your snark. So that only happens maybe once a slot or once a minute or once an hour, whenever, how often you want to do the settlement. And in some sense, the internal
Yes.
recursion will happen like millions of times, relative. Like it might be a 1,000,000 to 1 ratio in terms of workload between the internal one and the final one. Now, one thing that you're right, we should be concerned about, especially in the context of low latency proving, is we also want this wrapping to be reasonably low latency. Now, the good news is that these continuations, they're themselves snark proofs. Like they are themselves like small. So as an example, if you look at risk 0 or SP1 from succinct, like the continuation is itself a stock. So it's you could actually put it on chain.
Yes,
So
I know it's small in it's small in size. Yes, I see.
yes,
I know that the
exactly.
final wrap is happen very very small in the number of times. Yeah, so maybe we don't need to design another chip for it. Yeah. Okay. I got
Exactly.
it.
You could use the general purpose chip, which you've already built, the V0 chip, and that will be good enough. Or you could use
I see.
GPUs. Exactly.
I see. Okay, thank you.
Okay, so I guess there's two common like pushbacks on this approach that I get in terms of freezing. One is that people will tell you that the proof systems are continuously improving. So every year you have a proof system which is 3 times faster than the previous year, and that's totally valid. And because it takes time to design a chip, let's say 1 year, well, by the time your chip is out, then the proof system is kind of already outdated. There's something that's 3 times better. But like my response to this is that if we go down this route, you get 100x. And so, sure, you've lost on the 3x, but you're still, 100x faster. So you have still a net benefit of 33x.
But when you look at, for example, the announcement from Starkware or from the Folding folks, it's a 50x improvement, not just 3x.
Absolutely. This is a valid point. And so in some sense, you're making a bet here that, we're starting to get diminishing returns on the proof systems. And if you look at, for example, folding schemes, like Nova style folding, the constants are optimal. You have a constant of 1. And so it feels like we are starting to at least soon like start hitting a wall. I might be completely wrong, but I guess you're right, Mami, that we if there's another 50x coming next year, we should just wait and not build anything. And then the second kind of pushback that I get is, if we're fixing the risk 0 circuit here, what if there's a bug in the circuit? Now you have to trash your ASIC. It's garbage because it's fixed. And this is where formal verification, I think, can come in. And it's also another reason to have a fairly simple virtual machine here is that you can actually do formal verification on these simpler virtual machines. And one of the things that we're thinking about within the Ethereum Foundation is actually to dramatically boost the formal verification effort across the whole industry, because we're dealing with circuits and implementations everywhere. We have the ASICs, potentially ZK ASICs, but we also have ZK rollups that are going to have hundreds of billions of dollars, and we want to remove the training wheels, but we also want to make sure that we don't have these enormous bugs that could potentially be a systemic risk to Ethereum itself. And then we have the clients, the EVM clients, that could potentially be systemic because it could lead to consensus failures. And so, it's still early days, but where I and Vitalik and others are trying to push for this large scale competition to push forward formal verification. And so what I think is a good approach is basically to pick a specific circuit for RISC-V and make sure it's formally verified before you go tape out the ASIC. And actually, this is typical in ASICs. They will generally try and prove formally verified properties of the binary circuit, like the transistors and the wires, because even a single bug could mean that the whole chip is gone.
Justin, you mentioned ZK rollup in terms of source of bugs, but if they use ZK VM like RISC-0, SP1, Jolt, Nexus, the bug would be in GEF or REEF, not in the rollup itself.
Yeah, that's correct. So that's one of the great advantages of this the ZK VM abstraction, is that you can reuse the existing tooling and compilers and clients. And we are comfortable with the quality of GEF and REF, and we are comfortable with the Go compiler and the Rust compiler. These are kind of known quantities. The thing that is an unknown quantity is basically anything that has to do with circuits and below, so circuits and proof systems. And so this is what we want to minimize the surface area of, and what we want to have the highest diligence of on, which is potentially using formal verification. And so really the formal verification in the context of a ZK client that uses SP1, for example, would primarily be focused on the RISC-V circuit.
Another approach is that there are compilers that use SMT AST, so satisfiability model load theory, like CIRC, and those can generate both formal proofs and compile to ZK circuit. Like I think it's Ozdemir something, a Turkish guy who's doing a PhD at Stanford that's spearheading this effort.
I mean, that sounds great. If you could message me on Telegram, then it turns out that there's many different teams that have already started formal verification efforts internally. I think Scroll has looked into it, MATLabs has looked into it. Sounds like Tycho has also looked into it. So I think it'd be good to join forces.
So some audit company, there is Veridize. I think their CTO has a PhD in formal verification and offers formal verification for circuit. Quantstamp published some papers, and also Nevermind as a formal verification team. And if I were to formally verify some ZK, I would go to one of those three.
Amazing. I mean, yeah, let's touch base off chain, offline. Okay, this is, I believe, my last slide. So just trying to put some numbers on these ZK-VM approaches. So the ZK-VM approach, one of the big downsides is that you have very high proof overhead. So if you have like one cycle of RISC-V, you're going to need roughly 1 million cycles of RISC-V to do the proving relative to the native execution. That's maybe a couple of orders of magnitude relative to handwriting your statements. But as we talked about, the handwritten stuff is not necessarily friendly to hardware, but also not to developers or to formal verification. So I do think it is fine, a good kind of gambit to start off with this very large number in terms of overhead, which is being optimized quite heavily. So I believe like later this year, we're going to be in a position where the overhead is only 100,000x. Now, when you move to ASIC land, what you can expect, just rough back of the envelope, is 2 orders of magnitude improvement. So the 100,000x goes to 1,000x. And so one thing that is kind of, in my opinion, possibly like totally doable is that we have this 100 square millimeter chip, which is what I showed you on the camera. Just turn on the camera again. Basically, this image here on the slide is pretty much the same thing as this. And if you look at a RISC-V chip that are kind of manufactured, there's many of them, the die area is on the order of 0.1 square millimeter. So it's an absolutely tiny core, and that's roughly 1,000 times less than the die area that we have. And so what I'm hoping will happen is that we can have a full end-to-end prover that looks like this. You have the native execution that's done on chip, and then it kind of communicates to all the provers around it that almost on a cycle-by-cycle basis or with extremely low latency will produce a corresponding proof. And it's possible that this chip is going to be bottlenecked by power, right? Because the way that modern chips work is that if you turn on every single transistor all the time, it will just melt. And so this red area might be limited, let's say, to 10 megahertz or 100 megahertz. Let's say 10 megahertz. And if you want to run at the 1 gigahertz, well, you need to scale horizontally with these continuations that I talked about, with 10 different chips, each running at 100 different chips, each running at 10 megahertz. And that's the end of the presentation, and we're at the hour. So I guess I'll open it up to one last question, and then we'll have the post call discussion. Okay, looks like we have no more questions in the public part of the call. So I'll close it here and open the discussion for the post call.